Professor Marinos again. Over the last few lectures, we've explored how to calculate the equilibrium concentrations of products and reactants for a chemical reaction, given known or calculated values such as the standard Gibbs free energy of reaction and the standard enthalpy of reactions. But these known quantities are calculated or measured for fixed temperatures, so often 25 degrees Celsius. But of course, as you know, the temperature of the Earth can vary significantly from 25 degrees Celsius, and reactions aren't always occurring at that temperature. And this can change the equilibrium point of chemical reactions, sometimes quite appreciably. So in this lecture, we're going to explore a little bit about how temperature affects the equilibrium constant and how we can predict equilibrium constants at any temperature given known starting values such as the equilibrium constant and the Gibbs free energy of reaction at known temperatures. So let's launch right into that. By the end of this lecture, you'll be able to use the Van't Hoff equation to determine equilibrium concentrations for a reaction at any temperature. So to begin, I just want to give a brief example of where this might come up in aqueous geochemical systems. Let's consider a dissolution precipitation reaction, just a cartoon one, of AB solid, which dissolves into A positive and B negative in aqueous solution. And let's say that the K value for this reaction is much higher at a high temperature, at 300 degrees Celsius, than it is at 25 degrees Celsius. So what this means is that at the high temperature, you're going to have a lot of dissolution of this mineral. A lot of A and B will be held in solution at equilibrium conditions. But if you decrease the temperature, the water can hold much less of A and B in solution, and so the reverse reaction then becomes favored. You have formation of the solid from dissolved minerals. And this is what happens a lot in hydrothermally formed minerals, such as this beautiful turquoise right here. What happens is that water makes its way down deep into the earth where it's really warm, say 300 degrees Celsius. It dissolves a bunch of minerals, and then if that water comes back up to the surface, that water cools as it comes to the surface, and the reverse reaction is favored, and you have deposition of new minerals, such as turquoise, in the cracks of the rocks where this water is moving in. So in this lecture, what we want to address is why does K change, and how can we predict K? So let's figure this out. So if we know the equilibrium constant at one temperature, K at one temperature, and we want to know it at a different temperature, we can arrive at that by knowing how K changes as temperature changes. So dk dt, how the equilibrium constant changes with respect to temperature. So that's the goal. That is what we're trying to aim to develop an expression for. So let's see how we can get there using equations we already know. I'd like to first start off by writing the formula for standard free energy of reaction, which again is the standard enthalpy of reaction minus the temperature multiplied by the change in entropy. And now you'll recall that the Gibbs free energy reaction, not the standard free energy, but the actual Gibbs free energy reaction at equilibrium is 0. And that's also equal to the standard free energy plus RT times ln K. So we can write 0 equals the standard free energy of reaction at equilibrium plus RT ln K, where K is our equilibrium constant for the reaction. And so we can now just reshuffle this a little bit and write this as the standard free energy of reaction equals negative RT ln K. Okay, and now let's use this formula for the standard free energy reaction that we just wrote above, namely the standard free energy reaction equals the enthalpy of reaction minus T times the change in entropy. And we're left with this equation. RT times the log of the equilibrium constant equals the enthalpy of reaction minus the temperature times entropy. Now, just divide through by RT on both sides, and we can come through and cancel, and we end up with an expression where the log of the equilibrium constant equals the negative enthalpy of reaction divided by RT, so the gas constant times temperature, plus the change in entropy divided by R, the gas constant. Okay, so now where can we go from here? Well, we have k isolated on one side. It's in its logarithmic form, but that's still useful for us. Let's just take the derivative of both sides with respect to temperature. And so on your left-hand side, you have the change in log k with respect to the change in temperature. So the change in the equilibrium constant with respect to the change in temperature, which looks a lot like our goal, equals the standard enthalpy of reaction divided by the gas constant times temperature squared. That's just a straightforward application of the power rule for differentiation. And then this is a constant. Delta S over R doesn't have any t in it, so its change with respect to t is 0, so we can just cancel that out. And so now we have an expression, d log k over dt, which looks a lot like what our goal was. Let's just say this is close enough. This is what we call the Van't Hoff equation. Or at least this is the derivative form of the Van't Hoff equation. And this relates the change in k to a change in temperature. So how can we actually apply this? So I'll just rewrite this differential equation again. The change in log k with respect to temperature is the standard enthalpy of reaction over R times temperature squared. And this is a pretty straightforward differential equation to solve. So you can accomplish this just by separation of variables, the oldest trick in the book for solving differential equations, just by multiplying through by dt on both sides. So you've ended up with all the t containing terms on one side, on the right-hand side, and all the k containing terms on the left-hand side. Okay, so we started out that we know an equilibrium constant for a reaction at a given temperature. Let's call these K1 and T1 respectively. And we want to determine K for a different temperature of our choosing. Let's call these K2 and T2 respectively, with K2 being the unknown that we're solving for. So now let's look at the right-hand side of this equation. If we want to know the total change of the right-hand side as you go from T1 to T2, we can simply take the definite integral from T1 to T2. And we know also that this is equal to the definite integral of the left-hand side, going from K1 to our unknown K value K2. So just integrate both sides with respect to the differential that exists on each side. The left-hand side integrates simply to log k, evaluated between K1 and K2. And the right-hand side integrates by application of the power rule to the standard change in enthalpy divided by the gas constant, multiplied by -1 over temperature, as evaluated from T1 to T2. Okay, so just evaluate both sides. Left-hand side evaluates to log of K2 minus log of K1. The right-hand side, you can first just factor out the constant. So the enthalpy of reaction over R, you can factor out, and then evaluate -1 over T from T1 to T2. That will just evaluate to -1 over T2 plus 1 over T1. Now, the left-hand side of the equation again, you can rewrite this as just log K2 over K1 due to the properties of logarithms. And this is the final form of the integral form of the Van't Hoff equation. So using this equation, you can set T1 to the temperature that you know the K value for. K1 is that K value. And you can set T2 as the temperature you want to determine the reaction constant for. And you can use this to determine K2. You just have to rearrange this equation algebraically to arrive at an expression for K2. Okay, so let's just work a real simple example problem. Say we have a reaction with a K value at 25 degrees Celsius of 830. And we have a standard enthalpy of reaction at 25 degrees Celsius of 1.283 kilojoules per mole. What is the equilibrium constant of this reaction at 75 degrees Celsius? Let's figure that out. So I'll first start by just rewriting the integral form of the Van't Hoff equation that we just derived. That is the log of K2 over K1, and again we know K1 and we're trying to solve for K2, equals the standard enthalpy of reaction, measured at T1, over the ideal gas constant. And again, of course, it's very important that you match these units. You must match the ideal gas constant to the units that the standard enthalpy is in, either kilojoules or joules. Or if you're dealing with some chemistry from the 1800s, maybe it's in British thermal units, I don't know. Multiplied by 1 over T1, the initial temperature, minus 1 over T2, the temperature that you want to determine K for. And again, we said in the problem, K at 25 degrees Celsius was 830. And the standard enthalpy of reaction was negative 1.283 kilojoules per mole. And what we want to do is we want to determine the K value at 75 degrees Celsius. So what is this number? So now let's just use this Van't Hoff equation and plug in everything that we know into the equation and then solve for the one thing that we don't know, which is K2. We know that temperature, we know that temperature, we know the enthalpy of reaction that's going to go into the formula, and we know the gas constant, and we know that K value. So yep, we just need to solve for K2. So let's plug everything in. To start off, we have the log of x, the thing we're solving for, K2, over 830 equals the standard enthalpy of reaction, negative 1.283, over the ideal gas constant. Since we're in kilojoules, the ideal gas constant is 0.0083145, multiplied by 1 over the first temperature, 298.15, that's 25 degrees Celsius in Kelvin, minus 1 over 348.15, that's 75 degrees Celsius in Kelvin. So, okay, this is just plug and chug in your calculator. The right-hand side of this equation comes out to negative 0.0743, which equals the log of x over 830. So to get rid of this log, just exponentiate both sides, and you end up with x over 830 equals e to the negative 0.0743, which plug that into your calculator, you end up with 0.92. Multiply both sides by 830 to arrive at x. X equals 770, approximately. I rounded a little bit, but that's fine. And so we've solved our problem. We've identified K2. X is K2. And so K2, the K value at 75 degrees Celsius is 730. That is our new equilibrium constant for the new temperature of our system. Great. Awesome. Go Van't Hoff. So I just want to wrap up by reviewing Van't Hoff's equation in its integral form, which is the form that you'll most often use as you're doing thermochemistry. And the central principle of Van't Hoff's equation is that you can determine an equilibrium constant, K, for any temperature if you know K at one temperature and you know the standard enthalpy of reaction for that temperature that you know K for. So in this equation, on the left-hand side, you have the natural log of K2. This is the equilibrium constant at any temperature that you're normally wanting to solve this equation for, divided by K1. This is the equilibrium constant that you already know. So normally you're solving for K2, K1 is already known. Come over here, standard enthalpy of reaction is the standard enthalpy of reaction that corresponds to the temperature that K1 was measured at. This is known. The ideal gas constant is known. Temperature 1 is the temperature for which K1 was measured at and for which the standard enthalpy of reaction was determined at. And temperature 2 is the temperature that you want to solve for. So you just plug in everything except the only thing you don't know is K2, rearrange algebraically to solve, and you've arrived at your equilibrium constant for any temperature. So that is the premise of the Van't Hoff equation and how you can determine how equilibria change as temperature changes. Okay. That wraps up our review of basic thermodynamics. I hope this has jogged y'all's memory about the thermodynamic tools that you can use to understand chemical equilibria. In the next few weeks, we're going to take these tools out of the lab and into the real world to understand how real-world environmental aqueous geochemical systems behave. So, can't wait to get muddy with y'all. See you then.